All right, let's take a look at homework 5. So in the first problem, I want to represent 650 as a sum of two squares. So capital R of n is the total number of ways of doing this, and we prove the formula 4 times tau of n1, where n1 is the product of the good primes, the primes that are congruent to 1 mod 4. And I want to find all the representations using the factorization of the n in the Gaussian integers. So let's go back to the example we did in the notes. I think I did 3250 as one of the examples. So the first thing we'll do is just factor it completely. And so it's 2 times 5 cubed times 13. And then keep going into the Gaussian integers. So 2 is 1 plus I, 1 minus I, 1 plus 2I, 1 minus 2I, and these are each cubed. 2 plus 3I and 2 minus 3I. And let's break that up as a W times W bar. Okay. Now, I think in the example I did in the lecture, I just was looking for primitive representations. So in general, what we're going to do is just write down some selection for W, so maybe 1 plus I, and then the conjugate would have the 1 minus I, and then we could have a 1 plus 2I, let's say, and then the conjugate would have a 1 minus 2I, and so we would then have to have a square here, and then 2 plus 3I. There's an example. And then W conjugate would be 1 minus I, 1 minus 2I. It'll have 1 plus 2I squared. So when we multiply them, we'd have 1 plus 2I cubed coming out, and a 1 minus 2I cubed coming out, and then a 2 minus 3I. Okay, so what do you get? You just take out a calculator and compute this. So I get 45 plus 35I. Or you could think of that as 5 times 9 plus 7I. So that's one of your non-primitive representations. And then W conjugate would just be the conjugate. So here we're doing 3250 as 45 squared plus 35 squared. An imprimitive representation. So that's one way. A second way, 1 plus I, we could go 1 plus 2I squared, 1 minus 2I, 2 plus 3I, and I multiply that out and see, what did I get? Negative 55 plus 15I, another imprimitive representation. Something like that. So here we got 3250 is 55 squared plus 15 squared. And then we get into the primitive ways of doing it. But you might ask, well, why don't we use these same things here, maybe change that to a 2 minus 3I. Well, you're going to end up with one of the same things. The thing to remember is that 1 plus I is an associate of 1 minus I. So you don't get as many different representations when you have a 2 as one of the factors. You're going to just be repeating yourself if we try to change this to a 2 minus 3I here. But to get distinct ones, we could have no 1 plus 2I, and I'll just throw everything into the 1 minus 2I, like this. And that's what we do to get the primitive representations. So this one we did in the notes. And what am I getting for this? 1 plus I, 1 minus 2I cubed, 2 plus 3I, get 1 minus 57I. And then the fourth way, we can throw everything into the 1 plus 2i cubed. 2 plus 3i, and that one, we got 21 minus 53i. So here we're getting 1 squared plus 57 squared and 21 squared plus 53 squared. And let's see, does that coincide with the total number? The total number should be 4 times tau of n1. So n1 is 5 cubed times 13. So 4 tau of n1 is 4 times tau of, let's write it down, tau of 5 cubed times 13, which is 4 times 2, 8. So you have 32, but remember with the plus or minus signs and the symmetry, there's really just 4 distinct ways of doing it. And those were the 4 we found. And then finally, we've already done this. We found all the primitive representations, and so all you want to do is just confirm this formula. So for 3250, 3250 again was 2 times 5 cubed times 13. And so according to the theorem, there should be 2 to the 4th representations. So k is 2 here, and r of n is 2 to the 4th, which is 16, which means really just the 2 distinct ones we already found. All right, let's move on. Problem 2. Show that if n has a primitive representation as a sum of 2 squares, then so does any divisor of n. So here you just want to use the theorems. So we have one theorem that says n has a primitive representation as sum of 2 squares if and only if what? N is just equal to n1, so a product of the primes congruent to 1 mod 4, or n equals 2 times n1. So just use that theorem. And I think that was theorem 5.4.4. 5.4.4 in the notes. Okay, so, well, if n has a primitive representation, then it must be of this type, and therefore what can you say about any divisor of n? And use the fact that this is a theorem that goes both directions. Problem 3. Show that any integer of the form 4 to the m times 8k plus 7 cannot be expressed as a sum of 3 squares. So the first integer that can't be expressed as a sum of 3 squares is 7. How would you do it? You've got 1 squared and 2 squared to work with. Well, you can't get up to 7 just using 1s unless you use 7 of them. And if I used a 2 squared, I'm going to need at least 4 terms. Okay, so you cannot represent 7 as a sum of 3 squares. So we claim that any number of this type, and let's do a proof by induction. On m. So we start with m equaling 0, and you let n be a number of the form 8k plus 7. For some k greater than or equal to 0, and suppose this is a sum of 3 squares. So if n is a squared plus b squared plus c squared, that would imply that a squared plus b squared plus c squared is 8k plus 7. And what does that mean? So now view this congruence mod 8 to get a contradiction. To show impossible. Okay, so now we are in the inductive steps. Suppose true for a given value of k, of m. Suppose true for m, and consider n to be of this form, 4 to the m plus 1, 8k plus 7, and suppose that this is a sum of 3 squares. Let's see what happens. And let's see if we can prove that the only way that would be possible is for A, B, and C to be 0 mod 2. So let's view this congruence mod what? Mod 4. Is mod 4 good enough? Think about that. What if you viewed it mod 4? What would the right-hand side be and what would the left-hand side be? So squares are either zeros or ones, right? So show A, B, C are all even, and then divide both sides by 4, etc. I'll let you, and then bring in the inductive hypothesis. Problem 4. Let's see, P and Q are primes, with P equaling 2Q plus 1, so that means Q is a Sophie-Germain prime. A is a positive integer less than P minus 1, and I want to prove that A is a primitive root mod P if and only if A is a quadratic non-residue mod P. Okay, so there's 2 directions. Let's suppose that A is a primitive root. What does that mean? That means its order is P minus 1. And I want to prove that A is a quadratic non-residue. Well, what is our test for determining whether something's a quadratic non-residue? We have the Euler criterion. So just use the Euler criterion. Try that out. And now let's turn to the converse. Converse. So in the converse, we're going to suppose that A is a quadratic non-residue. And so again, by Euler criterion, you've got a quadratic non-residue. You got this is -1 mod P. But what is P minus 1 over 2? That's Q. So now just ask yourself, what is the order of A mod P? So find order mod P of A. All right, it's got to be a divisor of the group order, and we've got this to work with, and we know that Q is a prime. So calculate the order. Problem 5. Apply the strong pseudoprime test 3277 to test for primality using the bases 2, 3, 5 as necessary. So in this one, use a computer to do all of your modular arithmetic. You can go to Wolfram Alpha. So we just start by factoring this number and just following the examples that I did in the lecture. I think we have some good examples. You can go back to the lecture notes from this section and use a computer to just kind of follow the test. Problem 6. Establish Korselt's criterion. So m is a Carmichael number if and only if m is square-free, and for any prime divisor of m, p minus 1 has to divide m minus 1. Okay, so Carmichael numbers are numbers that behave like primes in the sense that Fermat's little theorem holds for all values of a. So let's see. We got two things to show. So let's suppose that m is a Carmichael number. Okay, so that means that a to the m minus 1 is congruent to 1 mod m for all a relatively prime to m. And now, why must m be square-free if that's going to happen? So let's do a proof by contradiction. Suppose m is not square-free. So say p to the e divides m. We can do exactly dividing with e bigger than 1. So you got some prime divisor where e is bigger than 1. And let's let a, so the assumption here is that this is holding for all values of a. So I can choose a to be anything convenient. I'm going to let a be a primitive root. A primitive root mod p to the e. I can't choose a primitive root mod m because I don't know that m has one. But I do know that for this odd prime p to the e, there will be a primitive root. So let a be a primitive root mod p to the e, meaning that the order of a is p to the e minus 1, p minus 1. But we also know from this fact here that the order of a must be a divisor of m minus 1. So use that to get a contradiction. Use the fact that the order mod p to the e of a divides m minus 1 to get a contradiction. Okay, next, why must p minus 1 divide m minus 1? So at this point, we now know that m must be a product of distinct primes. You can't have any square factor. And I want to show that for any one of these primes, pi minus 1 divides m minus 1. So what does that do? Well, this starred congruence, just use the fact that star is equivalent to saying that a to the m minus 1 is congruent to 1 mod each of the prime factors of m. So that's just a Chinese remainder theorem. So being congruent mod m is equivalent to being congruent mod each of the prime factors. These are distinct prime factors here. Okay, so I think that should do it. So now we've got this is true, and what do you know about elements in here? And again, remember star is holding for arbitrary A, so think of an appropriate choice of A to get this conclusion right here. Okay, so that's one direction. Let me see if there's anything more to think about. I think for the converse, it should be straightforward. Let you just play with that, and you can ask me if you need help on the converse there. Okay, now verify that this is a Carmichael number. That's also just a calculation there. Problem 7. Show that any prime factor of the kth Fermat number must be of this form. So Fk is 2 to the 2 to the k plus 1. That's the definition of the kth Fermat number. We're assuming k is at least 2. So let p be a prime factor. So that means that Fk is congruent to 0 mod p, which means that 2 to the 2 to the k is negative 1 mod p. And so what does that tell you about the order of 2? I claim it identifies the order, right? That you know exactly what the order of 2 is just from this one equation right here. Okay, and then deduce that P is of this form. For some m. Why is that? So you know what the order is, and you also know that the order is always a divisor of the group order. So it's always a divisor of p minus 1. And that should be allow you to get this type of representation. And now we want to go one step further and show that in fact it must have that this value m must be even, and so it's of the form m times 2 to the k plus 2 plus 1. So this m is not the m we're going to get in the final answer, so maybe you put an m prime here. And what I want to do is use this fact here. So now that I have p of this form, so let's just think of this as being the second part, p is congruent to what? Mod 8. And therefore, 2p equals what? By our criterion we established. So 2p is plus 1 when p is congruent to plus or minus 1 mod 8, and so on. So you can figure out exactly what this equals, and now use Euler's criterion. Right, that will say 2 to the p minus 1 over 2, and you'll know what this is congruent to, mod p, and see where that takes you. Okay, and then use this fact in a calculator. You can factor the fifth Fermat number, do exactly what Euler succeeded in doing, because you're going to identify what are the possible types of prime factors. You're going to look at numbers of this form, m times 2 to the k plus 2 plus 1. So here k is equal to 5. So p must be of the form m times 2 to the 7th power plus 1. Well, what is 2 to the 7th power? 2 to the 7th power is 128. So you're going to look for prime factors of this form. And you don't have to go too far to actually find one just by trial and error. Problem 8. Let Q be 4 to the n plus 1. Prove that Q is a prime if and only if 3 to the q minus 1 over 2 is congruent to negative 1 mod q. Okay, so we have a test that you can use, but let's just go back to scratch and think about it. So suppose Q is a prime. Then what is 3Q? Find 3Q. Right? We did quadratic reciprocity. We should be able to calculate this because we know what Q looks like. Q is what mod 4? And so by quadratic reciprocity, you can flip it, dunk, and decide whether there's a plus or minus sign right here. And then you know what the value of Q is, mod 3, and so you can calculate this and then use the Euler criterion. Okay, that's one direction. For the converse, suppose 3 to the q minus 1 over 2 is congruent to negative 1 mod q. And my goal now is to show that the order mod q of 3 is q minus 1. And if you can do that, that proves that q is a prime, because the order must be a divisor of the Euler phi function, right? So that would imply that q minus 1 divides phi of q, and you can show that means q is a prime. So we did this in one of the theorems. Maybe it was Pepin's test. Q is a prime. Okay. Oh, you're sitting on my work, Smokey. Huh? You want to say hi to people? Ah. You put you down. Q is a prime. Yeah, I think that's good. Problem 9. Show that for any real number, square bracket 2x minus 2 bracket x is less than or equal to 1. Well, you can actually calculate that quantity on the left-hand side. Just say x is bracket x plus a little delta. Right? Oops. Where delta is less than 1. So it's its integer part plus this little bit extra. And then 2x would be 2 bracket x, that's a whole number, plus 2 delta. And so bracket 2x equals what? And there'll be two considerations right here. You can actually calculate it depending on the value of delta. Calculate this exactly. So you'll have two cases: if delta blah blah blah, if delta's blah blah blah, and that should make the result fall right out. And you just put it together. Okay, now I want to use that fact to prove part B. So suppose that P is a prime with P to the E exactly dividing the combinatorial symbol 2n choose 2, 2n choose n, prove that p to the e is less than 2n. So 2n choose n is 2n factorial over n factorial times n factorial. And then I want to calculate the multiplicity of p, so that's new p. 2n choose n. So that would be the multiplicity in the numerator minus 2 times the multiplicity in the denominator. And then we use our theorem that gives us the value of this multiplicity. So we have bracket 2n over p to the k minus 2 square bracket of what? Put it together and use part A. To get that this is less than or equal, so you'll put that together, to log base p of 2n. And where is that coming from? Well, you have to look at how many terms. For how many terms does this have a chance of being a non-zero quantity? As soon as p to the k exceeds 2n, this is always going to be 0. And so this is counting how many non-zero terms we have. And then you can use that to get this bound right here. Okay, problem 10. Prove that if n is relatively prime to k, then k is a divisor. So we had proven a theorem that says for primes, p is always a divisor of p choose k for any smaller integer k. And so this is generalizing it. If we don't have a prime up in the top spot, so n is an arbitrary positive integer, as long as the lower entry is relatively prime to n, we still have this type of divisibility criterion. So I think the neatest way of doing this is just to use this fact. N choose k, so if you haven't seen this before, show it. Show that n choose k is n divided by k times n minus 1 choose k minus 1. And then clear the denominators. So bring the k over here, in other words, and use what? Go back to Euclid, I think. See what that does.